Dear colleagues, I'm very glad that I have been invited to chair the first regular session of the conference Electronics 2024. The topic of the section will be electrical engineering. My name is Jožef Ritonja. I'm coming from University of Maribor. I'm professor at that institution. I am head of the department of the Institute for Electrical Power Engineering and head of the Laboratory for Electrical Machine and Drives. My primary research activities are design and construction of electrical machines, control of electrical drives, modeling, analysis, simulation, and control of power systems, and modeling and control of bioprocess engineering. So I'm working in this area already for 40 years, and now we will be together 1.5 hours, 90 minutes. We have 5 papers to be presented during this session. Unfortunately, till now, only 3 presenters are here. So it is not necessary to tell you that you have to stay in the prescribed time limit. You can talk as long as you want. So, but I just asking you to have presentation so understandable also for unfamiliar audience, not only for selected people. Okay, now we will start. Our first paper deals with, will you put, please? Our first paper will deal with harmonic filters for distribution power systems. I'm asking the presenter to come and smile. So I will see it now. So the title of the paper is, I will read it, Determination of Optimal Locations and Parameters of Passive Harmonic Filters in Unbalanced Systems using the Multi-Objective Genetic Algorithms. The authors are coming from University of Pristina and Kosovska Mitrovica and from University of Niš. The authors are Milos Milovanovic, Svetlana Raičević, Dardan Klimenta, Nebojša Raicevic, and Bojan Perovic. And the presenter will be Professor Dardan or Klimenta from University of Pristina, Kosovska Mitrovica. Please.
Dear Chairman, thank you for introduction, and I will present the paper Determination of Optimal Locations and Parameters of Passive Harmonic Filters in Unbalanced Systems using the Multi-Objective Genetic Algorithm. On the first slide, you can see plan of the presentation. I will introduce some elementary details about our study. After that, the design of passive filters, problem formulation, optimization algorithm also will be described in some details, results and discussions. And after that, I will say some words about conclusions drawn based on the results presented and some future directions. According to our work, introduction is consisted of 3 slides and what we did. In modern power networks, the presence of nonlinear loads and renewables is expressed and how to say examined in this paper. Generation of voltage and current harmonics, negative influence of harmonics, harmonic distortion, important indicator of power quality, implication of power harmonic flows, commonly used solution, technical and economic effects, And also I will say some words about the major advantages of power harmonic filters, possibility of resonance, and power harmonic flows are subject to readjustment. On this slide, the problem of optimal planning of passive filters, which are nonlinear in this case, non-convex, static, large dimensions, and multi-objective optimization problem will be presented. Techniques for solving of the problem, traditional, one analytical, linear, nonlinear, and quadratic programming, and the application of meta-heuristic methods will be presented. And in this paper, multi-objective generation algorithm is used. This algorithm is tested on the unbalanced and distorted 2 IEEE bus systems, standard benchmarks in this field of science, uncertainties of loads and the variations of the RLC parameters and frequency are taken into consideration. Verification of the results is performed by comparisons with the available results in the literature, and results were generated using the software DigiSilent. In this slide, we can see design of passive filters. I will not go to details, but what we can see in this figure 1, commonly used types of filters, single-tuned, first order, high pass, second order, third order, and C-type. Many types of this kind of filters can be found in practice. On this slide, you can see some equations related to single-tuned passive harmonic filters, and these parameters are considered in designing phase of this kind of filters. Problem formulation is given in the next 3 slides, because here we have a lot of formulas and some descriptions. I will try to cover them a little bit quicker, and I will say just some details about this formulation. Option is always to minimize something or to maximize. We have constraints, equalities or inequalities or both, and some aims to be generated at the end like solution to find somewhat what is optimal for the considered multi-objective problem. And you can see what is here. Here we have the problem is consisted from three tasks. That means minimization of total harmonic distortion in voltage, minimization of costs of filters, and minimization of voltage unbalances. And the fourth one is simultaneous minimization of total harmonic distortion in voltage, costs and filters, and voltage unbalances. These were the objectives of this modeling. Also, as I said previously, a lot of formulas are consisted in these types of studies, and I will not go in details about them. But you can see on this slide some equations related to equality constraints, to inequality constraints, control variable limits. For instance, inequality constraints are divided into 2 groups related to the first IEEE test bus system 519 and the second one 1531. optimization algorithms are presented in the next slides. Again, I will avoid to describe the known things about algorithms. Many of us knows details about genetic algorithm, and I will avoid to explain them in detail. But we said some words about the algorithms in this presentation. What is the main thing of each study are results and discussion of them. On this slide, we can see graphical presentation of IEEE 13 bus system, which is a radial and highly unbalanced system. And what is the main contribution of this work is analysis of nonlinear loads and appearance of harmonics due to existence of power electronics in this benchmark systems. You can see value of voltage. Linear loads are modeled by the series of RL model. Non-linear loads are treated as harmonic current sources. On the next slide, you can see some of attempts to verify our results. A very high degree of consistency was established, and the mean errors was lower than 5%. Results are in good agreement with some results already reported in existing and the relevant literature. Some of our results are tabulated. This table, table 1, outlines locations and parameters of installed filters. These filters are placed in these two benchmark IEEE bus systems, and more details is given in the paper which is already published in the journal Electrotechnica e Electronica. And I will also avoid to go to minor details and explain what is done. But this is related to placement and sizing of filters in these two previously presented IEEE test systems. Also, the table 1 also outlines some dependent variables and objective functions for the IEEE 13 bus system. What to say about this? We have one base case and 4 cases considered, and all that are compared to the base case which was without filters. Results shown on this slide shows Pareto front for the case 4, and A diagram shows actual values, while the B graph shows normalized values for objective functions. I said previously we considered 5 objective functions and try to find the optimal solution which satisfies all of them. Finding one optimal solution, this is reasonable for the problem of this kind. This slide shows on figure 5, you can see the total harmonic distortions in voltage levels of the IEEE 13 bus system with and without filters. In figure 6, you can see voltage profiles of for the same systems with and without passive harmonic filters. And again, to explain all this, I need a lot of time, but we will try to answer some responses after presentation. On this slide, we are moving from the simple system consisted of 13 buses to the one consisted of 37 buses. Also, this system is radial and highly unbalanced. That means consisted of non-linear loads. Linear loads are modeled like previously by a series of RL model, and the harmonic source is adjustable speed driver connected at bus 740. And some details about apparent powers A, B, C per phase, of course, are given together with the graphical presentation of IEEE 37 bus system. Again, without tabulated results in this kind of study, we cannot move ahead. In table 3, we have locations and parameters of installed filters. Again, 4 cases are considered and compared to the base one. Table 4 shows location and parameters of filters installed in this IEEE 37 bus system. Also, you can see some numerals circled by these red lines that represent some optimal solutions for this test system. Again, like in previous case with 14 buses, we have Pareto front case 4. Actual values are shown in graph A, while normalized values of objective function are shown on the graph B. Results on total harmonic distortions in voltage levels for this IEEE 37 bus system are shown in figure 9, and in figure 10 we have shown voltage profiles of IEEE 37 bus system with and without passive harmonic filters. This slide shows in the graph we can see the uncertainty distributions of input stochastic variables determine the uncertainty distribution of output variables of interest. What is interesting here, the efficiency of a passive harmonic filter depends on the system impedance at the PCC, as well as change in frequency and RLC load. This algorithm is used to obtain the statistical information for the output variables. You can at the bottom of this slide some recommendations from IEEE 1531 standard. That means capacitors are with tolerance plus minus 5%, inductors with tolerance plus minus 3%, resistors with the tolerance the same like inductors, and frequency with tolerance plus minus 1%. Also, table 5 outlines statistical parameters of total harmonic distortion, distortions in voltage levels at bus 740. You can see some results also circled for case 1, for case 2, and related diagrams comparisons for these distortions for levels for cases 2 and 1 are shown in these diagrams. Also, you can see some details presented on these diagrams on the upper right corners of each of them. And from all presented results, we can draw the following conclusions. It is shown that proper planning of passive harmonic filters, in addition to reducing distortions, can improve other technical economic performances, because each optimization is not only to find the best technical solution, also to get some economical benefits from optimal solution. That is the main aim of this study, and similar studies existing in the literature. The accuracy of the method used is verified using the software DigiSilent. It is found that RLC parameters of passive harmonic filters have a higher impact of the standard deviation of total harmonic distortion in voltage levels than loads and frequency, and this algorithm used in this case to any other distribution system with any types of nonlinear loads and renewable energy sources can be applied and will give optimal solution independently of conflicts between three different objectives. Future directions are listed at the end of this slide. Development and application of other meta-heuristic methods are possible instead of genetic algorithm, taking into account the change of other input variables such as magnitude and phase angle of harmonic sources, independencies, branches, etc., consideration of other types of passive harmonic filters, nonlinear load, and sources. Thank you for your attention, and I hope I presented this work in 15 minutes, and please, questions, do you have any question for me? But not related to defense and similar things. Thank you.
I just have first to say thank you to Professor Klimenta. He jumped into the line, so he was not prepared for this presentation. So other presenter was intended to be here, but just 5 minutes before he knew the information that he will be on the stage. So thank you really much. It was perfect. But we have some questions. So please,
I'm here.
we have a lot of time, and
I like questions.
yes, please. Are there any questions? It is really very interesting research, very important. It will be even more important in the future because of changing in the distribution system. Any question? Yes, please.
Welcome, please.
Thank you very much for your really very good presentation.
Thank you.
I only want to ask you who support your research? Is there some company or government or only the institute?
Our research is supported always by our government, because we have some funds on the annual basis given for research. Each of us dealing with science and research has, for example, $200 per month, euros per month for this. And maybe we sometimes remember our support at the end of acknowledgement, but I think this paper remains without this knowledge.
Yeah, but I think it's quite interesting for the economy also, you know.
Yeah, of
I
course.
Think, you know, in the future,
of
you
course.
have to ask, you know, some company or startup, you know, to support
this. Especially this research belongs to the new, how to say, new view to the application of optimization methods, because this research deals like some existing papers. Not there are no more than 10 papers of this kind now reported, because we deal with nonlinear loads, power electronics effect on distribution and microgrids, grids, and this is future combination of existing distribution systems with inclusion of renewables at a different power levels in networks, how to say, grids.
Okay, thank you so much. Because I think my presentation also have some links related to this one,
Yeah.
and we are missing, you know, the support. Thank you so much.
Okay, thank you very much for the process.
Yes. Yes, please.
Thank you. In the first part of your presentation, you showed us 3 cases. Could you tell me more about what are the dependent variable? Like what are the difference between these cases?
Which part of presentation
Can you go forward?
in
Forward.
this side to the beginning or to the result?
Forward. Go
Forward.
Yes, on the table part.
Table.
Yes, there is these 4 cases. And what would be the difference on each one of these cases to interpret the
Between
results?
these cases. For details about this research, you have already published this paper on the archives of Technica Electronica journal, where you can see all the details present. But differences exist. Look, these buses, 675. In each of these notes, you have somewhat changed, and cases are. What is this slide number? This is 20. The number. I have explanation for it. I will answer to your question after presentation.
Break.
Okay, thank you.
Yeah. Any question more?
Any question? Yes, or something? No. Then may I? Because we
Of
have
course.
time, so in
Of
other
course.
situation, I will
Yeah.
ask you to leave the stage, but now,
I like to ask and to be asked.
but now you have to to be here. So the problem is really difficult, yes, because you first you deal with higher harmonics
Yeah.
because of nonlinear loads, and after then additional to unbalanced power
Yeah.
system. Yes. So perhaps did you try calculate only to find the positions, the optimal positions of filters and the optimal parameters, also only for balanced system? Understand that only
Yeah,
take
yeah.
care about the higher harmonics, but you didn't think about the unbalanced system. Is the difference in the results, or are results similar?
Results cannot be the same because unbalances are somewhat which must be treated in different way, like previously problems. Also in the past, we considered problems of this kind mentioned by you, but now is really hard to find optimal solution, global one, and important is to note considered objective functions are in conflict. This is related to your question,
Yes.
meaning the improving the satisfaction of the function has an adverse effect on the other. That means it was not so easy to find optimal solution for this kind of problem.
Thank you.
The objectives in
It-
one.
it
This
is-
is like coffee.
It is very interesting. It was not agreed with us. So the question. So, but next question. So you find the solution for different topologies and parameters of power system. Yes, you
Yeah.
find the solution where is the
Yeah,
best place
yeah.
and where is the better parameters. And is this and what about the operating point? So if load flow changes, so also the parameters must be changed, or they can stay the same?
Change.
Then you have to
It
measure.
changes. Power flows change. And what was dime to show first with simpler power system, and that was IEEE 13 bus system, and after that we moved to the complex one consisted of 37 buses. And if you have systems with with higher number of nodes, of course, it is computational efforts are how to say must be at a higher level than in the case of simpler system.
Okay, thank you. And just last question: used a power factor, excellent for simulation.
Well,
Yes, yes. Are you satisfied with this software?
Also, I forgot to remember we had some codes written in the MATLAB, and
okay.
some simulations are made in combination with
This was the
DigiSilent
question,
and
yes,
MATLAB.
because it's very
Because
difficult.
the first author of this paper is expert for this codes and to application of beta heuristic to such kind of problems.
Okay.
Okay.
Thank you.
Thank you, Chairman.
Thank you.
This was
Yes.
nice questions. Thank you very much.
The reason, I think the reason for your torture is not here. Or is he already coming? Yong is not here. Okay. Then we will have the third presentation, very interesting. So I'm really, really
I'm here.
here.
You hear me?
The title, yes.
You hear me? Yeah. I'm Yong.
Oh, it will be online? Okay.
Yeah,
Then-
I'm online.
Oh, nice.
I'm sorry. So,
Oh, thank you. Then start, please.
Oh.
Yes, I will just introduce you. The title of the paper is The Frequency Regulation Control Method of Large-Scale Distributed Energy Storage System in the Smart Grid.
yes.
There are authors, many authors, but the presenter will be Yong.
Yeah,
Son?
yes. Yeah, I'm Yong.
Oh, thank you. Thank you. Please start. Yeah.
Thank you. So, can we begin now? Okay. So good evening, esteemed chair, distinguished judges, colleagues, and guests. My name is Yong, and it's my great privilege to present our research. Our study is titled The Frequency Regulation Control Method of Large-Scale Distributed Energy Storage System in the Smart Grid. So thank you very much for being here today. Before we begin, let me briefly outline the main contents of our presentation. From the introduction to conclusion, what we will explore our research findings step by step. Please join me in reviewing the agenda to understand the journey we are embarking now. Sorry. The part two now that we've seen the roadmap for our presentation, let's dive into the first step on our journey, the introduction. So any question?
Yes, slides.
What?
Your slide.
Oh, sorry. Oh, first of all is the background of our research, which can be concluded as 4 points. With the increasing penetration of renewable energy, such as wind and solar power in powered systems, the challenge of frequency control in the grid is becoming more severe. The net two is traditional frequency regulation methods struggle to cope with the intermittency and uncertainty of renewable energy, leading to a decline in grid stability. And three is distributed battery energy storage systems we call BESS. BESS have emerged as a new technology that can effectively address grid frequency regulation.
Slides, please.
What?
Slides.
No, all the content is on this slide. So currently existing frequency control methods for BESS have several limitations and more optimized control solutions are needed to improve system response performance. So next is our solutions. 4 points overall. Number one is we propose a sparse communication network-based frequency control method for this, reducing reliance on high bandwidth communication. Number two, we use dual-layer model predictive control with a nominal controller for normal conditions and an auxiliary controller for uncertainties. Three is optimizes frequency regulation, improving base response on the various battery capacities and states. And four is effectively handles communication delays and uncertainties, enhancing system robustness. The part two is what we do. The following are several important studies related to frequency regulation and phase, along with the research gaps addressed by this paper. State feedback for frequency control. Our study used state feedback controller for base struggle with handling uncertainties in complex grids. Distributed multi-base coordination. Distributed control improves frequency regulation but relies heavily on high bandwidth communication. Consensus algorithms and frequency control. Consensus-based methods enhance coordination but perform poorly on the high renewable energy penetration. Number four is model predictive control for frequency regulation. MPC optimizes frequency control but has high computational demands. This comparison clears the difference between traditional methods and the innovation in the proposed method, highlighting its advantages in communication, control, uncertainty management, and robustness. The traditional method has 6 features based on single-layered control for consensus algorithms, reliance on high bandwidth real-time communication, insufficient response to uncertainties caused by renewable energy, poor robustness under complex grid conditions, slower response, low accuracy, and suitable for low penetration for low load fluctuation scenarios. And our proposed method is based on dual-layer model predictive control, based on a sparse communication network, reducing communication demand, addresses system uncertainty through the auxiliary controller, greater robustness, suitable for high penetration renewable energy environments, enhanced frequency regulation response speed and accuracy, suitable for high penetration renewable energy and complex load fluctuation scenarios. The frequency control method for distributed based on sparse communication network is proposed, reducing reliance on high bandwidth communication, combined with the dual-layer model predictive control system. The nominal and auxiliary controller work together on to optimize base frequency regulation performance, particularly excelling on handling uncertainties. The two main benefits our proposed method we can see is optimized frequency control with sparse communication, Number two is enhanced robustness in handling uncertainties. A dual-layer MPC significantly improves the system's regulation performance in dealing with frequency fluctuations and uncertainties, making it especially suitable for scenarios with high renewable energy penetration. Our dual-layer model predict control mode is composed of two parts. The first one is nominal controller, and number two is auxiliary controller. The nominal controller predicts control signals based on the system state without uncertainties, and the auxiliary controller handles the actual system's uncertainties and adjusts the nominal control signals. The objective is minimize system frequency deviation and the control costs, ensuring frequency stability under various conditions. BNC's paper uses a two-layer MPC approach to generate frequency control signals for the base. The approach achieves load frequency control while optimizing the cost function. The related constraints of the base and the power system are considered in optimizing the cost function. In the proposed frequency control method, thermal power plants and distributed battery energy storage systems are coordinated through a fuzzy logic controller. This method effectively regulates grid frequency under communication delays, preventing excessive system frequency fluctuation caused by the delays. The fuzzy logic controller adjusts the power output of thermal power plants in real time based on base output signals and the grid frequency deviation signals. Now, part two is our simulation analysis. Figure 5 shows the schematic diagram of the improved IEEE 39 bus test system. This test system includes 10 generators, G1 to G10, and the 3 wind farms, WT1 to WT3, with a total generation capacity of 60 megawatts, located at bus 4, 26, and 16 in areas 1, 2, and 3, respectively. Each wind farm has an average generation power of 20 megawatts. Figure 6 shows the wind speed fluctuation for these areas. Area 1 and 2 have 2 base aggregators with capacity of 4.68 megawatts per hour and 4.25 megawatts per hour, respectively, each controlling 5 distributed base units. Figure 8 and figure 9, figure 7 and figure 8 show the deviation in frequency and timeline power of the test systems. Last part is the conclusion of our research. 2 benefits of our research can be summarized as: number 1, advantages of dual-layer MPC. Compared to traditional MPC, the dual-layer MPC performs better in reducing frequency deviations and timeline power deviations, enhancing system regulation performance. Number 2 is response speed and power output. Distributed base response faster under various load conditions, providing high sorry. Number 3 is handling uncertainties. The method demonstrates greater robustness in dealing with the uncertainties brought by renewable energy resources such as wind and solar power. Number 4 is coordinated control. Through coordinated control between base and the thermal power plant, the system improves frequency regulation efficiency while reducing the impacts of communication delays. This slide shows our future prospects. Coordination of different energy storage systems. Future research can further explore the coordinated control of different types of energy storage systems, such as battery storage and the flywheel storage to further enhance frequency regulation performance. Validation in practical applications. It's recommended to conduct large-scale tests in real power grids to verify the effectiveness and robustness of the dual-layer MPC method in handling complex grids. 3 is optimization for high renewable energy penetration. In the future, this method can be further optimized to adapt to more complex environments with high penetration of new renewable energy. That's all for my speech. Thank you.
Thank you to you.
Sorry, I didn't put my slide. Sorry.
I have to, as chair, I have to say you that we are very disappointed that we saw that you prepare a lot of slides, you spent a lot of time for this, but so in future you have to be careful on this. Presentations are always bi-directional, so don't repeat such mistake. So please. Now
Sorry.
questions. There are some questions now. Please don't smile. Just okay. You are talking about the frequency control. First, I thought that you were thinking about the secondary frequency control, about the control with the one main controller in the system, PI controller. But so later, I found out that you are talking about the load frequency, primary frequency control. Is this true?
Yeah. Yes.
It means that this is the control of the frequency on every generator. So
Yes.
static characteristic. We are talking about this kind of control, frequency control. If the frequency drop, then you have to increase the government, the governor outlet. Does this mean, this is the question now, do you hear me?
Yeah, I can hear you, but you can hear it
Does
clearly.
this mean that you need every battery storage for every generator where you would like to control the frequency?
Yes.
Okay. What about
Sorry, I can't hear.
what about the power of this battery storage we are talking? How big are these batteries? What is the power?
Power?
Yes.
Oh, sorry, I can hear you. That question moment.
Yes. So I will ask you again, what's about the power and capacity of these battery storages?
Sorry, I can answer that, but I can chat with my team member to have a discussion.
So we can ask you on the emails if you have any other questions.
Yeah.
Possible?
Yes. Yes.
Okay. Then I will
Thank you.
say thank you to you again. Yes, it was fine presentation, but only one was missing. So thank you once again.
Thank you.
You will continue. Please, finally. And now just prepare it. One presenter is still missing from Saudi Arabia. Is he here? No. Is he on the? Did he? Nobody is sending. Okay. Okay. So the third presentation will be is entitled Airborne Wind Energy in Turkey with focus on wind resources, life cycle assessment, and techno-economic analysis. There are three authors from the University of Biležić, from Electrical and Electronics Department, and the presenter will be Associated Professor Emrah Dokur. Yes, thank you. Please start.
Introduce. Hello, everyone. My name is Emrah Dokur. I am an associated professor in Department of Electrical Electronics Engineering at Bilecik University. The university is in Turkey, Türkiye. Our countries has been changed name, Türkiye, the official name. The others names are Ahmet Emre Onay, who is my PhD student. The same department, and also Mehmet Kurban, who is a professor in the same department. Also, he was a supervisor when I was a PhD student. Today, I am going to talk about nearly 15 minutes, but I think we have a time. I am not sure.
For 2 papers. So
Okay.
not more than 10 minutes.
Okay. I am pleased to present research on airborne wind energy in Türkiye, particularly with focus on wind resource, life cycle assessment, and techno-economic analysis. I am talking about this. Let's dive into the details this promising technology. In today's presentation, I will begin with a brief introduction to airborne wind energy, and we will then move on to literature review, followed by an overview of the wind data assessment. And after that, we will explore the results of life cycle assessment and techno-economic analysis. Finally, I will conclude with a discussion of our findings and their potential of implication of Türkiye, the land space, Turkey's energy land space. Our study centers of airborne wind energy, an innovative technology that captures of high altitude, the power of high altitude winds, which are more consistent, stronger than those at ground level. The research specifically evaluates the airborne wind energy systems in Hatay region of the Türkiye, a promising area for this technology. The motivation behind is this study is to address the limitation of traditional wind turbines and explore how airborne wind energy can contribute to sustainable energy sources. To achieve this, we applied a combination of wind resource analysis. There are 3 steps of our study. First of all, we talk about the wind energy potential analysis, and then life cycle assessment, and finally, I will conclude the techno-economic analysis. The literature highlights several key aspects. I would like to talk about the shortly literature review. The literature highlights several key aspects of airborne wind energy. One of the major findings is the lower installation costs of airborne wind energy systems when compared to traditional horizontal wind horizontal axis wind turbines. This makes airborne winds a potential more cost-effective solution, which a critical, significant for sustainable energy development, particularly in region in Türkiye. Studies have shown that airborne wind energy systems not only have lower installation cost, but also offer a higher capacity factor and greater operational flexibility, making them more attractive option for large-scale renewable energy development. So the first step of the study was assess the wind data. It was 12 months wind speed data for Hatay region. And we utilized the parameter estimation methods for the two-parameter variable distribution and for the accurate wind speed modeling. Before the installation of the wind energy conversion systems, you need to model to wind speed characteristic. You need this one. First of all, you collected the data, nearly 12 months you need to collect it, and then you modeled using by some statistical approach, such as two-parameter variable distribution, gamma distribution, some distribution functions. You need to model it. We especially focused on the two-parameter variable distribution because of the two-parameter variable distribution is commonly used in this area. But another challenge is that there are some parameter estimation methods in to determine two-parameter estimation of variable distribution. We use 14 parameter estimation methods to compare it. As you've seen in this figure, the Hatay region of the Türkiye, the data was nearly the altitude is 100-meter altitude data. There are 14 of them which are the generally used method in the literature. These are the parameter estimation methods for the two-parameter variable distribution. Also, these abbreviation will be used in the study for each method. The Hatay region, the wind potential map of the Hatay region, 100-meter data. And now, in this graph, the bars represent the actual wind data, while the lines corresponding to performance of the various parameter estimation method. The goal is to find the method that most closely match the actual data. Among of 14 methods we tested, and novel energy pattern factor method and maximum likelihood based models emerged as the most accurate in the estimating wind parameter estimation methods. But we don't understand directly the graph, the model performance. You need to use some performance metrics such as root mean square error, or correlation coefficient, and also we need a wind energy error. We calculated in them. When it compares the calculating the wind power, the power density method delivered the lowest error and was the closest to actual measured values, making it the best choose wind power estimation. And talking about another factor of the wind data assessment, there are error values assessment as the next steps. And as you've seen in this table, there are ranking based on these error values, performance metrics. For wind energy error, the best performing method was power density, as I mentioned that. And other methods best performing was the maximum likelihood based method, alternative maximum likelihood, also modified maximum likelihood method is another performance. And for the next phase, we look at how all these methods perform. And if you remember the first graph, the right side, the small figure, we talk about closeness of each method, the actual wind data. So these are the points that are closest to farthest the actual wind data. And the table shows the number of closest point to actual wind data. And if you, based on the wind speed characteristic only, the novel energy pattern factor method performed the best here. But another is wind energy intensification method. It is proposed 2020. It has been a recently method in the literature also. We performed it, we modeled it. And this is also final evaluation in the first step. So for the wind power density calculation, as you've seen in the figure, wind power density is 64.39 gigawatt hour per meter squared per year. And the closest one is the power density method, followed by the energy pattern factor method in this study. And the next phase is the life cycle assessment. We conducted a comparative life cycle assessment, LCA, of airborne wind energy versus traditional wind turbines. Both of each were evaluated at 50 megawatt capacity. There are some key findings that we will be discussing in the next presentation. The finding shows that the summary airborne wind energy systems have a lower environmental footprint, requiring fewer materials and generating less greenhouse gas emission throughout the life cycle. This makes airborne wind energy a more sustainable alternative long run. This is the life cycle analysis, the methodology. Our methodology, the three main steps, consist of the three main steps: defining the project, goals and scopes, life cycle inventory analysis, and life cycle impacts. We use some softwares. These are namely OpenLCA. Also, we use another Simpro, Umberto, and EcoChain like this. We need to adapt to some data. And this is the first phase of the life cycle. There is need to have a breakdown of airborne wind plant, all the materials, all the parts. Well, of course, all the parts are not shown in here, but there are many parts are included, the systems. Also, we included our software analysis. This is more or less the main parts of the wind energy plant. I would like to share the results of masses comparison. This is the comparison of the masses for traditional wind turbines and airborne wind energy systems. So it can be seen that the airborne wind energy systems mostly uses much less material for the energy produced. And the second graph, the right side graph, is the mass per megawatt hours. And here also the airborne energy plant uses much less materials. The largest amount of materials is used in the foundation, the base ground in the both of the blends. And the closest value actual is the power generation apparatus, PGA, or nickel parts of this nickel. And this is, and we look at the mass comparison for only airborne wind energy systems, energy plant. And this is the breakdown of the masses for each part for foundation, ground station, landing apparatus, cabling, and etc. And also I would like to talk about the climate impacts. Looking at the climate impacts for both airborne wind energy and horizontal axis wind turbine, again, the use of less material airborne wind energy systems shows its advantage in here. It has generally lower climate impacts. For example, on the left, it shows the global warming potential. It's almost half of what is in horizontal axis wind turbines. And we will look at the graph on the right. It shows the cumulative energy demand, the energy demand per megawatt hour produced. And again, airborne energy is almost half what is horizontal axis wind turbines. And And for the climate impacts for life cycle, again, it is the same results in there. And I would like to talk about the final steps of our studies. In the final part of our study, we evaluate the economic viability of airborne wind energy. The systems throughout the techno-economic analysis, the results indicate that airborne wind energy systems offer the lower operational costs, shorter payback periods, and greater financial benefits compared to traditional wind turbines, making them an economically attractive option for future energy investment. And I would like to share these climate impacts for life cycles. First of all, the CAPEX, the capital expenditure and operational expenditure has been calculated using this part of shown in the graph that are also used in the life cycle assessment study. These are used to calculate their first investment costs and operational costs. For this airborne wind energy systems, aircraft parts and transformer take us the large share in CAPEX, and while maintenance is the main consumer of OPEX. This slides compared to airborne wind energy systems, especially I would like to add to this slide. We use some recent articles in there. And these slides compare it. For example, power coefficiency, airborne wind energy systems share a power coefficiency 53 and 55 with a relink factor. Whereas horizontal axis wind turbines, as you know, the operates as 35 between the 35 to 40 percentage coefficiency. And maybe we can talk this one. And this is the general techno-economic model we used in the study. I know it's very small, but I would like to explain the results. Annual revenue of the $5.5 million. Also levelized cost of energy $2.2 per megawatt hour. Net present value of the $5.4 million. And also I would like to share to interval rate return is calculated to 148 percentage of our studies. Also, these are the simulation results of the studies. Finally, I would like the main conclusion are the airborne wind energy system provide and reliable, sustainable, some social economic benefits. Of course, maybe lots of people think about the disadvantage. What is the disadvantage? Maybe we talk about after the conclusions. Only I would like to focus to you about the life cycle assessment, wind energy potential analysis, and finally techno-economic analysis. These results are the initial parts of our studies. Thank you for your attention. Thank you, our colleague. Thank you, dear Chairman Ritonja. Thank you very much.
Thank you for your interesting presentation. I just hope that my flights will not be more expensive. So in future, because of airbornes, what will be the heights? So you talk about 100 meters.
Exactly.
But in reality, you are thinking much higher.
Yes, you are true. This is very much higher at 100 meter and much higher. We can use it. There are lots of disadvantages in if you use the 100 meters up to 100 meters, you can see to tether fault problems and drone height problems in there. We collected the data, especially this area. 10 meters and also 50 meters we have, and we correlated the 100-meter data to simulate it. And the first step of our study, we used the this data.
Yes, thank you. Thank you. Questions? Please.
Sorry, for the installation, I'm interested in about, you know, to how big, you know, the windmill or your new solution is in the size, how you put it on 100-meter high. And after that, how do you think to get back the energy down to the ground, you know?
Exactly.
Because you speak about megawatt.
Exactly.
And
Yeah.
that's all, you know.
Yeah. I agree with you, actually. There are the main problems is that transmission, the electricity transmission. During the electricity transmission, there are some challenges in this area. Some installations, not methods, the installation techniques, for example, a balloon and drones kite like this. Yes, true. There are some problems in there. I would like to explain, especially, I would like to edit some videos, but okay, you don't have time. And yeah, okay. Yeah, and then maybe after the presentation, we will talk about the more details about this. But airborne, finally, I would like to say airborne wind energy has significant potential for harnessing the high altitude winds, but it is also focused on some challenges. And so these include issues with especially autonomous controls and stability issues, the kite problems, the tether problems. I would like to edit this.
Thank you.
Thank you very much.
Now we'll go to the last presenter. We have exactly 18 minutes. The last presenter is coming. You can see immediately from the University of Debrecen, from Faculty of Engineering. And the title of the paper is Low Frequency Electromagnetic Measurements of Spectrum Modulated Brushless Direct Current Motors for Educational Purposes. There are 4 authors. Professor István Balajti, Cornel Ilyos, István Balajti, and 3 authors, sorry, and Geza Hushi, and the presenter will be Professor István Balajti. Please.
Yeah, thank you very much, Mr. Chairman. This presentation about my student thesis work, he finished it last year, and my task was only to supervise his work and channelize, you know, the knowledge on that orientation where I thought, you know, is most important. And the low frequency electromagnetic measurement of spectrum modulated brushless direct current motor for educational purposes. It also was very important to all of this technical study is not only from technical purpose, but from educational purposes also required, because we recognize that we not have enough time with technical laboratory and hours, and we have to be as fast as possible to be efficient. Now let's see, you know, the contents. A few words about the brushless motor introductions, you know, and the motivation also, the background, the electromagnetic compatibility standard, you know. We use this standard for all environment in Debrecen area. We have more and more economy, and we have to develop a new method for different kind of standard. And also we have to keep the standard as efficient as possible. And so we have to reduce the electromagnetic smog in our environment. At least we have to train our students to be efficient on this one. Now let's see the brushless direct current motors. They are the most popular recently in all of the environment, as we can see. Even today, we have seen a few drones which use, you know, such kind of motors. Okay, it's very important to speak about the control, because the tricks and how can you manage efficiently energy is in the control. Okay, you can see, you know, the electromagnetic spectrum measurement, which is my favorite subject of you speaking, key electromagnetic emission issue, and we also focus here the why spectrum modulation is needed here, why we use it, okay? And of course, after that, we have, you know, some test result, which a lot of test results are published in our paper. However, not everything is published. And we see there are a huge field of interest for future work. Of course, we can see, you know, we use the Rode-Schwarz test equipment, the spectrum analyzer, and also the most powerful national instrument data acquisition system. You have to know today, in the electromagnetic field measurement subject, the national instrument, one of the biggest company of the world, and the main production facility is located very close to Hungarian Debrecen town. Now see, you know, the motivation. As you can see here, oh wait, we have to, okay, see. As you can see everywhere, in the industry, in the robots, all kind of robots, you know, consumer electronic, the drones we have seen today, you know, electric vehicles and computer devices. We have it everywhere. So it's very important. These BLDC motors have advantages: customizable, cost efficient, and low maintenance required because brushless, okay? They have some shortcomings. Of course, you know, this many advantages has some cost requirements. So they are usually more expensive. And also the controller system and all of the design have to take care to prevent the magnet, you know, against the heat, because the heat is reducing the magnetic field power. Okay, why the electromagnetic emission interference is one important key issue today, you know. Okay, we not want to pollute the environment with electromagnetic shock. However, it's also, do we not want to waste energy, you know, to pollute it. We have, you know, the civilian and military standard to fulfill it. And also there are a few new type of standard under development right now, you know, where we also have to contribute in the future. And as I mentioned, the main issue for us, or the same issue, the educational purposes, you know. We want to develop some kind of procedure to accelerate this so important motors development, teaching process, you know. And also it was a very, very good motivation for the student, you know, to go to the conference, make a paper, you know, to work with. And let's see, what about, you know, the BLDC drives? Okay, everybody knows there are rotors, and the rotors usually permanent magnets, okay, north, south, bingo, it's nothing special. We have a stator. We have here 3 stator, you can see, and they are 120 degrees from each other positioned. Of course, they have some wires, you know, which change the magnetic field. And of course, we have, you know, some special controller. And this is a trick, how to control it, you know. And of course, all of the advantages they have, we can exploit it, you know. And we also can see to the control system here, you know, the T-starter. And also we have, you know, the transistor switch and the semiconductor switches, which can produce the required current for the wires, you know. And it looks like the system itself is very simple. So only one big issue here, the microcontroller programming, how to manage the stuff. And here the control types. It's well known that, and it's already from the 1960 or 17 is distributed, the trapezoidal control, which is called, you know, 6-step control, okay? And the other one, much more advanced, the field-oriented control by aligning the magnetic field to maximize the torch. This is a 2-1. And of course, you have to see, you know, how the A, B, and C should be controlled. There are many versions, you know, for the 6-step. But, you know, the field-oriented control, the most important. And we have, you know, seen today are 2 starters, okay? First, we have to, the equations and the control system, reduce it, the complexity. And the first one, using Clark transformation, from the 3 axes, we reduce, you know, only 2 axes. And how can we do it? We can do it on such a way to one one of them, you know, the axis will be balanced. Okay, it's technical. So if it is balanced, you can have a nice one. After that, the other trick, what you have to exploit, to the output torch highest when the rotor and the stator feel perpendicular. See, this is the key, you know. So sine and cosine. Okay, and in this case, the path transformation used from stationary to rotating stuff. And you can see this equation also. All of the details is produced, you know, in Riga, Latvia. From here, you can find it, it's perfectly works. Here, the other part of the measurement is electromagnetic spectrum measurement, you know, electromagnetic operation. Okay, all kinds of measurements should be reliable, stable, and if it is possible, we have to reach the maximum signal-noise ratio. This is the simplest way to carry out the measurement. Of course, you know, there are some very tricky and very advanced methods where you can detect the signal below the noise level. And this method also suitable for this one because the method using the small vectorial stuff, you know. So you can add, summarize the vectors in the longer time to integrate it, okay? And here you can see the university, my favorite, electromagnetic spectrum of operation. For engineers, this is the best one here, you know. Okay, now let's see. What kind of emission we speak about? Okay, we spoke about already the compatibility, the interference, okay, when the different motors are started to disturb each other, the emission, and the key here, like we today already heard about, the impedance, okay? Because the load and antennas and all kind of work should work, you know, in the matched impedance, you know. Here we can see the impedance, wave impedance, and the wavelength relation. And in the electromagnetic field, the radio, microwave, we are very, very leisure because we use, you know, the antennas and the sensor system with the electric field, you know, very convenient, suitable, well developed. However, here, the antenna system and the impedance is very critical, crucial one. So it's a different science. And the electric field do not have huge antennas. So we have to go here for the magnetic field measurement and exploitation. And here we get the point, you know, to why we need a spectrum. And basically, one of the findings is that today morning we heard about the drone, you know, warfare and so on. But from electromagnetic emission point of view, it's also detectable that the simplest and the cheapest motors are give you such kind of huge, very high peak, you know. We will see some example, we also measure it. And you can detect it, you know. Okay, the question is, how far is it should be? But it's also would be done. Also, the very important to the pulse wide modulation, the carrier frequency, it could be different one, you know. And the key here also, how can you spread the spectrum in the frequency one, you know, allocation. And the simple different phase combination, you have to make a much more sophisticated, where you give, you know, the perpendicular of the magnetic field to each other. However, it's a very complex. So you can change the frequency, the phase, and so on and so on. So you have a very complex equation. And after that, you will find to the huge peak, you have a right or possibility to mess it in the frequency band, you know. And also there are a few papers here, you know, when you can find more details. And here you can see our simplest version, the commercial drive, used everywhere, you know, have, you know, the power supply, the control system, and the drive itself, okay? And after that, we also have our design, you know. It's also, both design was developed by with our student, you know. And here you can see the unique spectrum drive solution. So you can see the power inverter here. Okay, you send you the back electromagnetic field sensors here. Also the gate logic, you know, to switching. And also, you know, the CPU here, you know. And of course, you can go in the paper and can find all of the details if you want to repeat it. And here, the first one, you can see, you know, it was built during, you know, the 3D printing. the students are like the 3D printer because everywhere in the universities, this also even not mentioned, but it was developed and also was produced with the 3D printing. However, you can see this is aluminum, you know, here. And it's protect, you know, the electronic field, but the magnetic field is completely can go through in it, you know. And you can see there's some technical parameters also. You can the diameter, the resistance is the key here. We have also other cool, and we have, you know, the receiver, the Rode-Schwarz receiver, spectrum analyzer, and as I mentioned, national instrument stuff. And here you can go, what is it? Somehow I can check it. Mom, no. Which was this? I want to show you now to it rotates. Again, wait this. Okay, and sorry for. No, it should work. Today it's already, we tried it. Discard, and that's it. You are right. No, where is it? Basically, this is a big film. Can you see? This is a coal B, you know, where it was handmade also. And here you can see the motor. Basically, this is an advanced one. And this is a SSM modulation. And it's also start to rotate, you know. It's really works. You can see here. Okay. And we have two types of motors, you know. Okay. Here the old version, you know, the traditional motor, it also rotates. And here the result. And let's go back, you know, for my laser printer. So you can see the SSM is off, okay? And also you see the duty cycle. Here I put the duty cycle, 60%, and we have 70% and 80% also. And you can see we detect precisely, you know, the frequency of 40 kilohertz, you know, with this 60% duty cycle. And also, when it was a 60% and we use the SSM modulation, we were able to reduce at 10 dB the emitter power. Okay, good. So the reduction is then 63%. Go to the next one. It duty cycle 30%, and you can see this is much higher, you know, the SSM peaks because we have 10 times more modulation frequency of the control. Here you can see, you know, 60, 70, 80, how they are connected to when it's not SSM modulation and we have modulation. And of course, you know, the duty cycle is 80% is give huge energy and you can concentrate it here. And here the national instrument data acquisition device. You also can see the big one, the traditional motor, and the blue one with the distributed one. Also, you have a different PRM of the motor. We also tried. It is shifted in frequency, okay? Here, you know, you even see that 70, 60, 80%. So it also looks like to the SSM modulation helps a lot. And the findings, the education potential examined successfully. So the student passed, you know, and got, you know, the mark. Also, the measured emission reduction is up to 80% at 40 kilohertz in some cases. The measured emission between setup is large. So it depends on which kind of setup you use, which kind of antenna. The ME capable of the oriented field. So it's compatible with the field-oriented control system-related solution. Improved emission performance at the measured frequency, we can detect and can show it's operational. The SSM efficiency is under certain condition is very useful to use. And the future task, better data collection, method development, digital connection to the instrument, like in the NI solution, more measurement, wider ranges, setting, calibration against standard. We not really made on the details of this one. The loaded motor versus unloaded motor measurement. Today we have seen, you know, some connection. How is it important and how is we have to be managed somehow. The future improvement. First, the question is one of yours will be the first one. Okay, but what is the distance when we can say it? The answer is that we need, you know, the wired antenna with higher gain for magnetic field, not the electrical field, because the phased array antenna for electrical field is perfect. However, very problematic to use, you know, wired antenna. Also, we can use the high temperature semiconductors. It's a hot topic today, and it's really sensitive for electromagnetic field. So it's can extend, you know, the large stuff. And usage of phased array of magnetic field detection. If you go for the medical instrument application, you will find a few solutions. And of course, we need a EMC data collection system for low frequency, which is one of the hottest topics today. And I hope next year we can inform you about our result. And right now, thank you very much for your attention. And my radar is open for your question. Thank you.
Thank you very much for your presentation. Question? Any question? I will not force anybody because we are in lack of the time. So thank you once again.
No, it's okay.
Oleg, if you are thinking that we already had all kinds of problems and we finished with the problems, then you are wrong. Our technicians succeeded to establish a connection with the fifth presenter, and we will have one presentation more. So this was the reason to be so fast with you. Therefore, we will shorten a little bit coffee break, and we will delay the start of the next session. So we will start 10 minutes later. So it means 20 before. Okay, now I will just introduce my colleagues. So the title of the paper is an enhanced FFT-based algorithm for improved phasor estimation. There are 6 authors. Gul Said, Anwar Ali, Musaid Al-Hussein, Khurshid Aurangzeb, Emnavid Ankhan, Anas Khan. Authors came from Kingdom of Saudi Arabia, United Kingdom, USA, and India. And I asked the presenter, Khurshid Aurangzeb, to start with the presentation. Please.
Hello everybody, and welcome to this presentation. Okay, so can you see the slides clearly? Okay, so let me first introduce.
And video, everything. Thank you.
Okay, thank you. So let me introduce myself first. My name is Anwar Ali, and I am lecturer at Department of Electronic and Electrical Engineering, Swansea University Bay Campus. And I'm going to present our paper Enhanced FFT Algorithm for Phasor Estimation in Dynamic Power Systems. The outline of this presentation is first I will introduce my paper. Okay. Then phasor estimation challenges, objective of the study, literature review, methodology, enhancement of FFT for the phasor estimation, some mathematical formulation, then simulation result, and total vector error, and at the end, conclusion. Introduction. So basically, phasor measurement unit, we call them PMUs. They are very critical for real-time monitoring and stability in modern power systems. And in dynamic conditions, power system lead to instability in magnitude and frequency. So large errors we have in phasor estimations. So this paper proposes an enhanced FFT-based algorithm to improve this phasor estimation accuracy using modified quadrature rules. So here, like we have an original signal and we have a reference signal. So at the sender side, normally, like our reference signal has certain phase difference with our original signal normally has certain phase difference with the reference signal. And then we calculate this phase difference at the receiver end. And we estimate like how much is the difference between our reference and original signal. So for the phasor estimation, like the traditional techniques used, that is DFT, discrete Fourier transform, which has many drawbacks, like with spectral leakage and fast dynamic condition, it has this issue. The second technique is TO, which is teaser energy operator. And the third one is EO, angle shift energy operator. So these two techniques, they handle fast dynamics, but they produce large errors during frequency shifts. So the need is for more accurate, reliable, and fast methods for real-time phasor estimation. So our objective is to improve the accuracy of PMUs under dynamic conditions using enhanced FFT algorithms and modified Simpson rule, MSR, for better numerical integration. So in the literature, normally for the phase estimation, phase detection, we use zero crossing detection, but this technique is sensitive to harmonics and noise. The second technique mostly used, that is wavelet transform. It's complex, but provide multi resolution analysis. The third technique is DFT-based methods. This technique is very fast, but limited under dynamic conditions due to spectral leakage. And we have some recent advances in phase estimation, that is teaser energy operator and angle shift energy operators. These two techniques, they need further refinement for fast changing condition, for the dynamic conditions. So our methodology is like we will use algorithms to enhance FFT technique. So we will use left point rule, midpoint rule, and right point rule for numerical integrations. Basically, these techniques, these are numerical integration methods which are used to approximate definite integrals. Like the left-hand rule, left point rule, it is used to approximate the integral by evaluating the function at the left end point of each subinterval. Like we normally divide our function into 3 subintervals. So we have left point rule, midpoint rule, and right point rule. And they normally approximate the function like on the left-hand side and the midpoint and on the right-hand side. Then we will use Simpson rule and modify Simpson rule to reduce the errors. So the modified Simpson rule, we call it MSR, that account for higher order error correction by incorporating the first derivative of the function and integration. It normally integrated the midpoint. So what is enhancement of FFT techniques like we are using? The paper defined new quadrature rules that improve DFT by calculating the probability density function using an integral approximation, applying quadrature-based FFT to process sinusoidal power signal with higher precision. And we are utilizing Simpson rule, third order quadrature rule, O3R, and MSR, modified Simpson rule, to obtain fine estimations. So what is Simpson rule? It approximates the power signal over a specific interval. Okay, and normally it applies these 3 quadrature rules: left point rule, midpoint rule, and right point rule. And as I mentioned, that we divide the signal normally in 3 intervals. So Simpson's rules, it's a combination of about 3 rules and forming the 3-point quadrature formula. So here's the mathematical representation of the Simpson rule. Modified Simpson rule, it's improved the Simpson rule and reducing the error up to 6th order. And here is the mathematical derivation, mathematical formulation for the Simpson rule. And there are a lot of mathematics behind these rules that is given in the paper. And the improvement of FFT based on MSR. So here is the improved technique, like we have this probability density function. Okay, and here pi d, that is the characteristic function, okay, of the random variable d, which is related to the probability density function through this inverse Fourier transform. And the interval here that has been divided into fixed intervals, hi, that is we have multiple fixed intervals, and then we analyze the signal using these techniques by dividing it into multiple fixed intervals. So here is the DFT estimation technique using the 3 quadrature rules: left point rule, midpoint rule, and right point rule. And here are some formulations for the estimation. Here in this slide, we can see the FFT estimation using quadrature rules. Like again, we are applying those 3 rules, those 3 techniques, and we estimate our signal error. Here is the ASEO technique, which is angle shift energy operator. And through this technique, we measure the phase and angle of the signal. Okay, but in this technique, like we have this sine square in the denominator, and it normally has very small value, so the magnitude error will be very large. Secondly, it cannot measure the signal in real time because the window needs to we need to move the window forward and backward, so we can't measure like estimate the magnitude in real time. Here is the total vector error. This is the equation for the total vector error. Like we are using different estimation techniques, and we are like measuring, we can use this formulation to measure the total vector error by using those different estimation techniques. So the total vector error, like applying those different techniques, for the DFT, the error we got, that is around 0.66. For the ASEO, it's 0.89. For the enhanced DFT, it's very high. For the MSF, it's the highest, and for the enhanced FFT techniques, is the lowest. So in the simulation results, like we got these errors, and for the enhanced FFT, the error is the lowest. So our device technique is the better one. So the enhanced FFT algorithm may provide faster, more accurate phase estimation in dynamic conditions. It improved handling the frequency variation and reduced the TVE, total vector error, improving the system reliability. So the approach is like it was a computational approach, and it's ideal for real-time PMU applications. So that's all from my side. Due to shortage of time, I was a bit fast. So actually we applied different estimation techniques to measure the total vector error, the signal we normally transfer. So we can use this technique on the PMU and can reduce the error.
So thank you very much for really interesting presentation. Thank you that you stay in time frame, really. Question? No question. Okay, and I will not force anybody. Thank you once.
Thank you for your attention and time.
Colleagues, especially Dardan, Klimenta, Emrah, Dokur, Istan Balaiti, Yong Sun, and Anwar Ali. Thank you for your presentation. They were really interesting presentation. Audience, thank you for your questions and for your patience. Yes, especially. And now, shall we go to coffee break? Yes. Thank you.